Reinforcement learning empowers agents to learn optimal behaviors through interaction with their environment, allowing them to adapt and improve over time. This dynamic field finds applications in robotics, game playing, resource management, and beyond, showcasing its versatility and potential. Within the realm of reinforcement learning, the concept of action spaces takes center stage, dictating the possible actions an agent can take and shaping their decision-making process. These actions can be discrete or continuous, each presenting unique challenges and opportunities for innovation and problem-solving. This essay delves into the fascinating world of continuous action spaces in reinforcement learning, exploring their nuances and practical applications in various fields. We'll navigate the intricacies of continuous control, comparing it to its discrete counterpart, and understanding the benefits and limitations of each approach. Along the way, we'll unveil powerful algorithms like Deep Deterministic Policy Gradient, twin-delay DDPG, and Soft Actor-Critic, which are at the forefront of this technology, equipping you with the knowledge to conquer the challenges of this domain and harness the full potential of reinforcement learning. In the world of reinforcement learning, actions speak louder than words. The choices an agent makes can significantly impact its success in achieving its goals. An action space defines the set of all possible actions an agent can take at any given state. This space is crucial for determining the agent's potential strategies. We categorize these spaces into two primary types, discrete and continuous. Each type has its own unique characteristics and applications. Discrete action spaces consist of a finite set of distinct actions. These actions are clearly defined and limited in number. Imagine playing a game of chess. You can move your pieces to a limited number of squares on the board. Each move is a discrete action. Continuous action spaces, however, allow for an infinite number of actions within a given range. These actions can vary smoothly and continuously. Steering a car provides an intuitive example. The angle of the steering wheel can be adjusted to any value within its range. The steering wheel's angle, represented as a continuous value, determines the car's direction. This allows for precise control over the vehicle's movement. This distinction is crucial, as it directly influences the algorithms we employ to solve reinforcement learning problems. Understanding the nature of the action space helps in designing more effective solutions. While continuous action spaces mirror the real world more realistically, they present unique challenges. The infinite nature of these spaces makes it impossible to explore every possible action. Traditional reinforcement learning algorithms, often relying on value iteration or Q-learning, struggle to cope with this vastness. Another challenge lies in the curse of dimensionality. As the number of action dimensions increases, the complexity of the problem grows exponentially. Finding an optimal policy amidst this complexity requires sophisticated algorithms capable of efficiently searching the continuous action space. To address the challenges of continuous action spaces, researchers have developed specialized algorithms that are both innovative and efficient. Deep Deterministic Policy Gradient, or DDPG, combines deep learning with the deterministic policy gradient theorem, enabling more precise control in complex environments. TD3, or twin-delay DDPG, builds upon DDPG by introducing a twin network and delayed policy updates to mitigate overestimation bias, enhancing stability and performance. Soft Actor-Critic, or SAC, takes a different approach by maximizing both the expected return and the entropy of the policy, promoting a balance between exploration and exploitation. By maximizing entropy, SAC encourages exploration and robustness, making it particularly effective in dynamic and unpredictable settings. These algorithms, leveraging the power of deep neural networks, have achieved remarkable results in various continuous control tasks, from robotics to autonomous vehicles, showcasing the potential of AI in real-world applications.